In this video, we're going to begin to look at motion in 2 and 3 dimensions. And so we're going to start with position and displacement. And we're going to draw two-dimensional and three-dimensional position vectors. And so we're going to explain all of this through our vector notation for particles and objects moving. And we're going to use a coordinate system to determine the direction and magnitude of the particle's position vector. And we're going to apply the relationship between a particle's displacement vector and its initial and final position vector. The concepts are pretty much the same as what we did in Physics 1. However, the math to describe these concepts are going to be a little different. So first, a position vector locates a particle in space, and this extends from a reference point or the origin. And so instead of just talking about x is equal to 3, meaning where it is along a line moving in one dimension, now we have a position based upon the origin, and it's going to represent all three spatial dimensions. And so that position vector, we are typically going to use r to describe the position vector. And r is going to have an x component, a y component, and a z component of its position vector. And so each of those components will be with the respective unit vectors I hat, j hat, and k hat. And so an example of a position vector, we could write it as -3, 2, 5. Now, a couple things here. We can write this two different ways. We can write it as the r vector is equal to -3 I hat plus 2j hat plus 5k hat, or we can actually, and this is vector notation that's used more in calculus, but we could say the r vector is equal to, and we get this bracket, -3, 2, 5, and then we close the bracket. So this is our position vector. It's just assumed that we write it I, j, k in that order. Either way, they represent the same thing. This is our position vector. And so what does that represent in three-dimensional space? Well, that means we're -3 along the x-axis. We are a +2 along the y-axis, and we are out 5 along the z-axis. And so that gives us the octant that we're located in. Now, just like in AP Physics 1, the change in a position is the displacement. So the change in a position vector is going to still be the displacement, and we'll call that delta r. Okay, and this is delta r is a vector because it's a difference of two vectors, initial vector taken away from the final vector. And we can write this as the x2 minus x1 times I hat, y2 minus y1, j hat, and so on. Or we can express this in terms of delta x, delta y, and delta z. So our delta r vector is just going to be the change in x, I hat, change in y, j hat, change in z, k hat. It's just subtracting the two vectors. And so we can continue this type of vector notation and take that into average velocity and instantaneous velocity, and keeping those calculus relationships between displacement and velocity. And so average velocity, we know, is the displacement divided by the time interval. So that's a definition that we had in physics before. Using that with this vector notation, now our average velocity is the change in the position vector or the displacement vector divided by the time. So it's pretty much the same thing. It's just a slightly different way to define it. Now we're talking about vectors. And remember, average velocity, even though it is an average, is still a vector quantity. And we can write this in component form, and we take the delta x I hat, delta y j hat, delta z k hat divided by delta t. So really that just gets us delta x over delta t, delta y over delta t, delta z over delta t. And you might think, well, why are we doing all of this? But this is actually kind of significant in that when we look at the velocity of an object, when we have it in vector notation, this tells us the rate of change of the x component of the object. And this is the rate of change of the y component of the object. And this is the rate of change of the z component of that object. And when you go on and learn more in calculus and the idea of partial differentiation, all of this comes into play. And it's actually very significant how they all intertwine here. But anyway, looking at an example of this type of velocity vector, if we have a particle that has a displacement of 12I and 3K, And it does this displacement in 2 seconds. Now this is our delta r here. And so notice we have no change in position in the y direction. We're only changing in our x and z because our displacement only exists in I hat and k hat. And since this happens in 2 seconds, we just divide those two, and so that gives us an average velocity of 6 I hat plus 1.5 k hat. And so this tells us that we are changing our position at a rate of 6 meters per second in the x direction and at a rate of 1.5 meters in the z direction. So instantaneous velocity, we know in the past with one dimension, that's just the derivative of the position function with respect to time. Well, the velocity at a single point in time, this is telling us the specific velocity at a certain point. And so if we have a position function, it is the slope of the tangent line there. But really, if we go back to how we define this, this is the limit as the average velocity takes a time interval that goes to 0, which that's just the limit definition of a derivative. And so really that becomes the derivative of the position vector. So whatever that position vector is, take a derivative and we get our velocity vector. So this is the same exact relationship that we've worked under in the past, just now we're talking about vectors instead of plain one-dimensional functions. And so to visualize the displacement in instantaneous velocity, look at a particle. This particle is moving along this path here, and as it moves along the path, its position vector changes. We have position vector 1 and position vector 2, so this is our displacement vector, the change in position. That vector right there shows us the direction in which we change our position, and the slope of the tangent line, or a line tangent to that curve, is going to give us the instantaneous velocity. The velocity vector is always tangent to the path of this particle, and this velocity vector, this is the x and the y components of the vector at that instant. So if we write it in vector notation, it gives us the x and y component, the I hat, the j hat. And once again, this could happen in 3 dimensions, so we could have a tangent surface here. A key, as mentioned in the last slide, is that the direction of an instantaneous velocity v vector of a particle is always tangent to the particle's path at the particle's position. So at that position in time, the tangent vector to its curved path is going to be the position vector. That's going to be the direction. And in unit vector form, we write that this is the derivative of each individual piece or component of the position vector, which it's dx dt I hat, dy dt j hat, dz dt k hat. Looks very similar to the average velocity, but what's the difference? We're taking the derivative of the position vector function instead of just taking an overall change. It's tangent slope versus secant slope. Just like the position vector, we can write the velocity vector in its vector notation where it has an x component, y component, and z component with their respective unit vectors. And that's where each of those are defined as the derivative of the respective position function. So Vx is defined as dx dt, and Vy is defined as dy dt, and so on. One note here is that a velocity vector does not extend from one point to another. It only shows direction and magnitude. Okay, position vectors and especially displacement vectors, excuse me, they actually do extend from a starting point to an ending point, but velocity vectors don't. They're just showing a direction and magnitude. The longer the vector is, the larger the velocity is, and the orientation of that vector shows the direction of the change in position. So let's look at an example here, and in this figure we show a circular path that's taken by a particle if the instantaneous velocity of the particle is given by this function 2 meters per second I hat minus 2 meters per second j hat, through which quadrant is the particle moving at that instant if it is traveling clockwise or counterclockwise around the circle. For both cases, we want to draw this velocity vector on the figure. So let's look at this first situation. If it's clockwise, that means we're rotating in this direction. And so we know if we're rotating in the clockwise direction, then our displacement vector is going to be tangent to the path, but more importantly, our velocity vector is going to be tangent to the path. And so it's always going to be pointing, if say we're in the first quadrant, it's going to be pointing this way because it's tangent and we're going clockwise. If we're in the fourth quadrant, we're going to be going this way. If we're in the third quadrant, we're going this way. And if we're in the second quadrant, we're going that way. And so we want to know which one of these gives us a positive x but a negative y. So which one of those vectors is going to the right but down? And that's right here when we are in the first quadrant. And so we can use this same idea to show that, well, if we're going counterclockwise, it's the opposite. We have to flip all of these arrows. And so which one is going to give us down and to the right? That's when we're in the third quadrant, right down here. Finally, we can take this same line of thinking into average acceleration and instantaneous acceleration. And we know average acceleration is a change in velocity divided by time interval. So that means we can just take a change in velocity vector, divide by time to get our average. And so we can then also say, well, our instantaneous acceleration, just like instantaneous velocity is a derivative, the instantaneous acceleration is also going to be the derivative or the limit as t approaches 0 of that average acceleration. And so we can rewrite that equation to say that, well, the acceleration vector is dvx dt I hat, dvy dt j hat, dvz dt k hat, and that gives us each little component. And we can even go a step further to say that, well, each component, we'll call that a sub x, a sub y, and a sub z, as long as we defined each of those as listed here. And just like before, to get the components of acceleration, we differentiate the components of velocity. And what does this represent? Well, these are the x and y components of the vector at that instant. And so we have an acceleration, and the acceleration vector shows us the change in velocity. It's not going to be tangent to the path like the velocity vector is. It's showing us the direction of the change of that velocity. And so just like with velocity, the acceleration vector does not extend from one point to another. It only shows the direction and the magnitude of that change in velocity. And so if we have a situation here where we have 4 descriptions of the position in meters of a puck as it moves along the xy plane, and so we have those 4 descriptions there, and are the x and y acceleration components constant? Is the acceleration vector constant? And so looking at this, we look at the function. Well, in 1, our position function, our x position function, is quadratic. So the derivative of that is going to be the velocity, which would give us a linear function. And the derivative of that would be a constant function, would just be a coefficient. In this case, it would be -6. Whereas in the y direction, if we take a derivative of that y position, we would get 12t, which would be our velocity derivative. That would be 12. So yes, the x and y acceleration components are constant in 1. Using that same scenario, we can find that, well, if the x and y components are both constant, then the acceleration vector is constant. So in situations 1 and 3, we see that they're constant across the board. But in situation 2, we aren't, because the x component is a cubic. So taking 2 derivatives, we still have a dependency upon t when we get to our acceleration vector. And so if there's a dependency on t, it's not going to remain constant. It's going to vary with time. And so that we see that happen in example 2 and example 4 in the x position. And so since the x is changing, the overall vector is changing, and it is considered to be not constant.